Hello, welcome to another episode of Skyshift, pioneering the eVTOL era. I'm very fortunate to have Richard Brown with me today of Sophrodyne Aerospace. Richard is an aerodynamicist, and we're going to learn more about that later in the show. So with that, Richard, I'll give an introduction to you. I'd like to hear a little bit about your background.
Sure. Well, it's a pleasure to be here, and thanks for inviting me, Martin. In terms of background, where do I start? I guess I started in the 1960s. As with many people in my generation, our formative years were those of Neil Armstrong and the Apollo missions. Although I was a little bit too young to see Neil Armstrong for myself, certainly Apollo 14 and 15 had a pretty formative experience. Were pretty formative and led me to go into some sort of aerospace career related to those experiences. I started off my career in South Africa, in fact, in the helicopter industry. And my initial ambition, I think, was to be a fighter aircraft designer. But through a slight administrative accident, which perhaps less said about the better, I ended up in the helicopter division, doing transonic aerodynamic calculations on the airfoils for the tips of helicopter rotor blades. And for a long while, I kind of struggled with this because I didn't really understand what the practical application of this work was. And my boss eventually came to me and said, look, you think you're doing this for theoretical reasons? Well, I'm going to show you something. And he dragged me through the factory, through all these doors of increasing security, until we came into this hangar. And there in the middle of the hangar was this yellow and green machine that was under construction. And that was like an epiphany. It was like that's the Star Trek movie where you come around the corner and there's the Enterprise under construction in front of you, right? And this was the Roy Falk attack helicopter that was under the process of being constructed. So we're talking around about 1980, 88, 89. And this aircraft was eventually produced. It was rolled out. It went into flight. And partway through the test program, they realized that its performance wasn't quite up to scratch. There were some handling qualities issues to do with lateral flight that they hadn't really been accounted for in the initial design. And by that stage, I was actually involved in more of a sort of overall aerodynamic analysis of these sorts of vehicles, and became very quickly apparent that the tools weren't actually working. We could do all these fancy calculations, but they were giving fundamentally flawed results. And that sort of started my interest in trying to develop computational tools for understanding how helicopters behave aerodynamically. And shortly thereafter, I changed path a little bit. I went into academia and started off a 30-year career in the universities around the world, I guess, and where I devoted quite a lot of attention to modeling the aerodynamics of helicopters and focusing in particular on interactional effects. So how the aerodynamics of the main rotors would influence the tail rotors, the tail fins, and all these sorts of issues. And for 30 years, that's essentially where I built my career around, the modeling and understanding of helicopter aerodynamics. A few interesting encounters along the way: vortex ring state, brownout, downwash and outwash, all these sorts of issues which are now coming to the fore in eVTOL again. And then when was it? It was 2015. I decided, okay, change of direction, been in academia long enough, seen that, done that. Let's try and do something a little bit more interesting. And by that stage, I'd realized that the academic path wasn't actually making that much of an impact on how industry was going about doing various things that they do, specifically the aeronautical industry. So with my wife, who's a very competent computer scientist, we set Sophrodyne Aerospace on the go. And we haven't really looked back since. That was 2015, so we're coming up for our 10th anniversary next year. And it's been 10 years of discovery and learning new things.
That's outstanding. You are obviously a pioneer. Helicopters really only became a thing shortly after World War II in terms of commercial use. So we have a lot of ground to cover here. And the first thing I'd like to know, what is an aerodynamicist?
Okay. It's somebody who studies the dynamics of air, as the name might suggest. So in other words, how air flows over solid bodies. And those solid bodies can be almost anything, from a power station to a hill to an aircraft. So the various tools that an aerodynamicist might use would depend on the application. You might find they use computational techniques, you might find they use wind tunnels, or you might find that they go all the way back and try to apply the fundamental theory to trying to understand just how the air flows over the body of interest. And the end result is normally trying to predict the forces on that particular body. And as such, then the aerodynamicist would feed their data through, let's say in an industrial concern, the folk who'd be most interested in speaking to the aerodynamicist would first of all be the structural people who want to know how strong to make the aircraft, and perhaps the performance guys and the flight dynamic guys who are interested in how those forces manifest in terms of roll rates and pitch rates and ability to fly so far, so high, and for so long.
So air is kind of a fickle thing. Most people would think of a helicopter taking off vertically in nice still air, but as that helicopter flies through the air, different climates, different temperatures, different altitudes, air around the aircraft has its own nature, and some of that is somewhat unpredictable. Would that be correct?
Yes, I think it was Einstein who said very famously that when I get to heaven, I expect to ask God two questions. First of all, what is the meaning of life? And secondly, why turbulence? And I expect an answer to the first question. So essentially that's it. Turbulence is one of the key features of the fluid dynamics of almost any of the objects that we're interested in describing. Yet the behavior within a turbulent flow field is so complex that it defies understanding. So we have these very basic equations called the Navier-Stokes equations, which describe how a fluid flows over a body, but they kind of give you the framework of what goes on. And the real issue is taking that framework and turning it into something which gives you reliable, realistic results for the loads on the aircraft, let's say, at the end. And that's the very problem that I was experiencing all the way back in the 1980s with helicopters. It was that taking the Navier-Stokes equations and turning them into some sort of intelligence about how helicopters operate just wasn't working out very well. So you're quite right.
Yeah, I have to say, just from my perspective, it's rather mind-boggling just in terms of, Mother Nature and the air and the atmosphere. It's a huge dynamic. And, obviously you started in the 60s. We've got some very familiar history with aircraft, conventional aircraft, as we understand it, conventional helicopters. But eVTOL is going to bring some new dynamics in terms of the configuration of the aircraft and how that air flows around
Absolutely.
it. What are some of the areas? This is unknown territory, and it's obviously unknown territory for you. Yeah. So as you look at these aircraft and your understanding as far as an aerodynamicist, what are some of the thoughts that come up?
The first one that comes to mind is that these are not helicopters. These are very different beasts. They have multiple rotors. They all produce their own independent flows. These flows then interact. And in that interaction with them, between the individual rotors and the other parts of the airframe, you get some very interesting effects. So my real interest is in bringing physical understanding into the eVTOL world. It's to take the fundamental fluid dynamic equations and produce sense from them, using numerical techniques, using basic fluid dynamic analysis. So what we tend to find is that in developing eVTOL aircraft, there are almost like two schools of thought. The one is that these are so completely new that we have to start from a clean sheet of paper. On the other side of the spectrum, you have the folk who say, well, these are just glorified helicopters in some sense. And anything we know about helicopters, we can just apply straightforwardly into the eVTOL world. And really the educational mission, sort of growing out of my academic career, if you like, is to try to say, hang on, we're actually sitting in the middle ground here, where what we know from the helicopter industry and from the long experience with single rotor vehicles has application into the eVTOL world, but it's not the end of the story. The eVTOLs that we see on the drawing boards are so interesting aerodynamically that they produce additional effects that we need to try to understand. So the two areas where I've tried to contribute most in the last years, the last months, have been, first of all, the idea of vortex ring state, which is a very interesting fluid dynamic effect which occurs within the wakes of propellers and rotors when they're in descending flight. Propeller wakes are inherently unstable, and that instability can lead to some quite severe performance issues, flight dynamic issues, if you like. We're going to talk about that a lot more, I think, in a future session. The other one has been the idea of what happens if you have an aircraft which is hovering fairly low above the ground, such that the wake from each of all these rotors can hit the ground and then spread out across the ground. Now, there's a lot of work that's been done in the past in the helicopter environment to do with that, but how does that work transfer across into the eVTOL domain, and what additional physical effects do we need to bring on board when we start talking about things like vertiport design? How close can these vehicles be to infrastructure? How close can they be to your granny when she's bringing somebody along to climb onto the aircraft to go on her flight to the local airport. And these are all issues which really need to be properly thought through and addressed before eVTOL becomes a viable and safe proposition.
So if I'm understanding you correctly, you're basically taking the existing knowledge we have and looking at the fact that we're also going to be entering a new era. So it's combining what we know with the openness, shall we say, of what we don't know.
Yeah.
And I'm curious, why did you pick the name Sophrodyne for your business?
Okay, yes. Now, what we wanted was a name that would encapsulate our ethic. And we really, really struggled. This was weeks of late nights trying to figure, big sheets of paper, trying to come up with a decent name. And my wife, one sleepless night, sat up and just went and browsed and came across this term, Sophrodyne. Now, what does Sophrodyne mean? It's an ancient Greek term which relates to the philosophy of mulling over something before you make a decision, of thinking before you speak, of making a considered judgment before you actually go and tell the world what you found. So Sophrodyne is this idea of considered thought, or think before you speak. So chop off the cine and stick on a dine, and what do you have? You have the power of considered thought. And that's where it comes from.
Yeah, I think it's a very suitable name because, in what you're articulating and describing, we clearly are in uncharted territories, but there are ways that we've had a history and can look at this. You mentioned earlier in your discussion about infrastructure and, of course, the landing facilities. How much study and how much effect does aerodynamics, as an aerodynamicist, how much regard do you have in terms of infrastructure, in terms of what these platforms are landing like, where they're located? What are the considerations that have to be looked at?
Yeah, okay. Well, this opens up a very interesting area for discussion, because what you tend to find again is that the industry on occasion can be dominated by people who have. Okay, let me try and phrase this in another way. It's so easy in this industry to come across silos, and the Vertiport community is a very, very typical example of that. So you have various folk. You have aerodynamicists, you have operators, you have pilots and folk who know how to fly these vehicles, or at least think they know how to fly eVTOL aircraft when they come about. And then you have folk who are perhaps architects who have exposure to the urban wind environment. And then you have folk who are metal and glass folk who can design you a very, very good-looking building. And the problem is, if each of these disciplines considers the problem in their own, you end up with a crazy elephant with horns, effectively. And the idea there is to try to bring these folk together into one room. And how aerodynamics influences the problem is essentially how these aircraft, when they come into land, what sort of influence on their environment do they have? So they're producing this blast of air downwards. That air, under certain conditions, will reach the ground, spread outwards. In spreading out above the ground, what actually happens to the infrastructure? Are you going to throw stones up against a beautiful glass facade of your fantastic vertiport? Are you going to blow people over in the car parks surrounding the vertiports, such as happened a year ago, just over a year ago here in the United Kingdom, in a very nasty accident down in one of the hospital heliports? If you are going to put infrastructure around a vehicle, what is the reflected character, if you like, of that airflow? The wake runs out, hits buildings and infrastructure around, comes back again and starts to interfere with the aircraft. Is that interaction favorable or is it unfavorable? We know from the helicopter experience that it's generally unfavorable. So when we design vertiports, we need to bring all these people into the room and educate them effectively about how all their disciplines kind of come into contact and interact with each other. And I think that's probably one of the most important hurdles to eVTOL safety that we need to encounter. It's to moderate this siloed nature of the industry.
So in terms of, we're not just talking the aircraft, we're talking the infrastructure. And of course, one of the other newer aspects of eVTOL will be the sheer volume number of aircraft. We're talking tens of thousands. And the other is, of course, access to city hubs. So far outside of helicopters for ambulance services, police, or possibly news, aircraft really don't fly at low altitudes through large cities. What's your thought with regard to studying weather effects within these cities? Because that too is kind of uncharted
Yeah,
space.
yeah, exactly. So I think we need to put a lot more emphasis on trying to understand how weather systems develop within the urban infrastructure, and then how those particular features of the urban wind environment influence the aerodynamics and performance of eVTOL aircraft. And there is quite a lot of work being done in that field at the moment, trying to understand how gusts that are created in the lee of large, tall buildings will interfere with aircraft that are trying to go down into the urban canyon behind those vehicles and perhaps land at some sort of landing site that's way down inside the urban canyon. Another interesting issue has been to see how the regulators actually cope with these particular issues. So, for example, EASA has a set of regulations where they're trying to work towards something sensible, and they take a very interesting approach. They put out some prospective regulations and they ask for comment, and it's been interesting to engage with the regulators on that aspect. So, for example, if you try to define a vertiport down in the bottom of an urban canyon, how do you define the limits of the volume in which aircraft are allowed to operate to get into that vertiport? And there again, it's very interesting. It's very easy to take an architectural viewpoint where you say, okay, we'll define a cone which has sides of 30 degrees and those will extend up to 45 meters, and then we'll have a flat plane which extends outwards. But it's very easy to forget the design engineering all this and to design an architecturally good-looking system into which an aircraft can't actually even operate, because you'll penetrate the vortex ring onset boundary or something like that. So again, it's this idea of education. It's to try to get the aerodynamic picture through to folk who perhaps are interested in developing infrastructure from a completely different viewpoint.
Whoa. So we have the aircraft, we have the infrastructure. I'd like to bounce back to the aircraft. Aircraft like the Osprey or the 609, they've kind of evolved this whole new concept. How have things historically been working out in relationship to the air surrounding these types of aircraft, which are a new configuration?
Mm-hmm. So, the Osprey in particular, the accident in 2000 where 19 Marines were killed during an exercise in the desert in Arizona has certainly had a very formative influence on my career. And it was a salutary lesson that if you thought that you understood helicopter aerodynamics in its entirety, you'd be completely wrong. In that case, it was vortex ring state which caused the problem. And what had not really been perceived up until then was the extent of the region of the flight envelope which was affected by this particular pathology in that particular case. So the pilot in coming into the formation of aircraft coming into land, the pilot in front missed his waypoint and started to come down at a rate which was pretty hectic compared to what would normally be considered in that particular aircraft. And the second aircraft in formation was coming down even faster, trying to formate behind his leader. And as such, went into such a high rate of descent that it looks like what happened is one of the V-22, for those folk who don't know, has two side-by-side rotors. And what seems to have happened is that one of the rotors went into the vortex ring state. The pilot didn't have the necessary means to compensate for that, and the aircraft rolled inverted and crashed into the desert floor, killing the passengers on board. But we learned from that, right? It was a very, very hard lesson, especially for the US Marines to take on board. And of course, the whole history of how they learned those lessons is worthy of several books, and has been. But again, within the eVTOL community, we need to watch out that we progress at such a rate that we actually understand what physical effects we're incorporating into these aircraft, and take proper cognizance of those effects early enough in the design process, so that by the time these aircraft enter service, we've largely cleared the flight envelope of any of these lurking pathologies that might be there.
Would I be correct? Most of the aircraft we're talking about are either rotor or propeller driven in terms of like jet engines, that type of stuff. This is what you're talking about applies to a very specific type of propulsion.
To an extent. Yeah, you're kind of skirting into the real unknown when you start talking about vortex ring state on, let's say, thrust thrust-based release, sort of, let's say something like a Lilium, where essentially you've got encased rotors or encased propulsors within a duct. How many research papers are there on vortex ring state in encased ducts? Probably 2. And there again, it's results taken on models which are probably this sort of diameter. So it's a real area where there's room for folk who are interested in doing fundamental research to get their hands dirty and actually produce a real contribution to the community, I think.
Now, are we seeing, we're seeing drones becoming very, very increasingly popular. Currently, I would guesstimate, the drones under 55 pounds, or thousands of them out there. We're eventually going to see these drones become larger and larger, 200, 500, 1,000 pounds. Will your area of study apply in the area of drones?
Absolutely. I mean, one thing that aerodynamics are often accused of is never giving people straight answers. And the way they often do that is by wrapping up the numbers that they produce in scale independent values. So you divide through the thrust by the disk loading, let's say by the dynamic pressure produced underneath the rotor, whatever it might be, some sort of way of hiding the true number in a way that you can apply those numbers to aircraft across the range of scales. So that's the way we generally proceed as an aerodynamicist. We say, okay, we do our experiments at one particular scale, but with care, you can actually extrapolate those results through into aircraft at other scales. So with a number of caveats, the kind of analysis that we do on full scale is applicable to drones, and likewise, we can do a lot of useful work on drones to understand what's going on bigger scale aircraft. As long as we approach that scaling process with a lot of care.
Yeah. So if I was if I was an eVTOL developer at a new aircraft or a drone, at what point would I look at bringing you in? Would I be bringing you in on the early design concept? Would I wait until I got a prototype? Or are you engaged throughout the process?
We tend to be engaged throughout the process at various levels of the whole design evolution. So yeah, in terms of mapping out concepts, that's where an aerodynamicist can come in incredibly useful in guiding away from certain pathological designs that we know are problematic, for example. When it comes to a design that's halfway through construction, then often there's quite a lot of palliative aerodynamic design to be done. So things are more or less cast in carbon fiber, but they're problems. How do you then address those problems? What sort of small additions can you make to change the aerodynamic characteristics more favorably? Then once the aircraft's in service, we end up with all these issues to do with compatibility with vertiports and the like. So aerodynamicists are involved throughout the process.
Well, Richard, when we spoke about this podcast, I said I wanted to break it up into segments. This topic is huge, and I think a lot of people very much, I consider myself a lay person. This is something new to me. There's other things I'd like to get into more detail about: vortex ring state, brownouts, downwash, and I'd like to focus on downwash and outwash for the next episode of Skyshift. I have to say it's been fascinating. My head is just ringing with trying to grasp, the concept of air. It's such a huge topic, just in terms of not just the size of it, the volume of it, and all the dynamics that it brings. So I thank you very much again for being on the show today, and looking forward very much to part 2.
You're welcome, Martin, and I look forward to talking to you again.